So first, before we do that, immediate question is, why don't we just do maximum likelihood over the model that includes CI? So why don't we keep CI as well in the model as something that we want to infer? We want to do a point estimate of CI in addition to a point estimate of pi, mu, and sigma. Because when we do that, when we write out the augmented joint likelihood where we include CI as a parameter we want to do a point estimate over, we take the log of this and we take derivatives and solve. What we would find is that we can optimize that very easily. We can get closed form updates for every parameter in the model, including CI. So that is something that can be done. But what we would find by doing that is we would end up with a hard clustering model, meaning that when we wanted to update a particular cluster assignment, CI, the maximizing that CI would lead to assigning the data point to the most probable cluster. So the maximum likelihood solution, or the map solution actually for CI, is to assign the ith data point to the most probable cluster. And so we would have a hard clustering algorithm. Our goal here is to integrate out the effect of the cluster assignment, which we're going to see when we do that in the EM framework is going to lead to a soft clustering algorithm that we anticipate should be more accurate and should be better than the hard clustering algorithm, because we've integrated out one of the unknowns in our model, so we have fewer potential local optimal solutions that we could converge to. So we're not going to derive the EM algorithm from scratch. I'll just give the outline in this lecture. However, we do, to repeat, we do treat these cluster assignment indicators as the latent data, the missing data in our model that we want to integrate over, so we include this thing. Therefore, we're going to use EM to maximize the log of this marginal likelihood, where C is gone, by using the log of this augmented or extended joint likelihood to help us do that. So let's look at the equation we saw last time and how it is modified for this particular model structure. Last lecture we saw that the generic EM objective looks like this. We want to do maximum likelihood over a model with parameter theta 1. So we want to maximize the log of the probability of data x given parameter theta 1, but that's difficult. And so we wrote this equality where we had this term here, which we called L. So this term we called L. And this term here was the Kolbeck-Leibler divergence between Q and the conditional posterior distribution. And we introduce the additional variable to our model, theta 2, and then integrate it out, and we do a two-step procedure. So remember, the procedures were to set Q equal to P, given that updated Q distribution, calculate this expectation, and then maximize this expectation over theta 1. And theta 2 is gone because it was integrated out. Now if we take this equality and we just write it using the Gaussian mixture model parameters and setup, we get something like this. So the log of the likelihood of all of the data given pi, mu, and sigma, because the data are assumed to be IID, that turns into the log of the product, which turns into the sum of the log of each individual likelihood. So we have a sum over all of the data of the log of the probability of each point given our Gaussian mixture model parameters. And now we introduce the hidden variable. So what we're doing here is you can ignore this first sum the first time you look at it. Just ignore this first sum. And now we're going to treat this term here as being like that term. And we're going to introduce C as this theta 2. So theta 1 corresponds to these parameters. Theta 2 corresponds to Ci. And because Ci is a discrete variable, the integral is going to turn into a sum. So when you have continuous variables, you integrate. When you have discrete ones, you sum. That's the difference. And so this integral over all the values that theta 2 can take turns into a sum over all the values that ci can take. But notice that, again, we have the data x. We have xi is mapping to x here. For theta 1, we're mapping our mixture model parameters to theta 1. For theta 2, we're mapping ci to theta 2 here, and we have ci. And then for the integral over all the values theta 2 can take, we're mapping that to the sum over all the values that ci can take. And similarly with the KL divergence. This term maps to this term. And now, because each of these individual terms are equal to each other, when we sum over all of the data on the left-hand side and sum over all the data on the right-hand side, again, nothing changes. We have the left-hand side is equal to the right-hand side. Let's now look at the EM algorithm for this model. Remember, with the EM algorithm, our goal is to first set the KL divergence equal to 0. So we have a sum over n different KL divergences here. Each KL divergence is calculated for, we have one KL divergence for one data point, and the ith KL divergence is equal to this term right here. And so to set the entire KL divergence to 0, we can set each individual KL divergence to 0. So we want to set Q of Ci equals K, which is our a probability of Ci equaling K, to be equal to the conditional posterior probability. So this should be also evaluating Ci is equal to K. So that's the first part of the E step. We set this distribution QCi equal K to be equal to the conditional posterior distribution of the ith data point being assigned to the kth cluster, given the value of the ith data point and given the parameters for the Gaussian mixture model at the current iteration. To do this, we use Bayes' rule. So Bayes' rule says that the conditional posterior is proportional to the prior of assigning the ith data point to cluster K times the likelihood of the observation of the ith observation given that it was assigned to cluster K. So we see that this term, the prior probability of assigning a data point to cluster K, is just equal to pi k, and the likelihood of the ith observation coming from cluster K is equal to a Gaussian, where we evaluate the likelihood of xi given the mean and covariance of the kth cluster. And then to turn that into a probability distribution, we simply normalize the right-hand side. So this is a proportionality. To turn this into an equality, we normalize this thing by dividing over the sum of all possible values that Ci can take, meaning we sum this numerator over all values k. So we take this, we divide it by the sum over all possible values for the cluster assignment, and we define this to be phi sub I of k. So this is serving identically the same purpose as with the weighted k-means algorithm. The only difference is that now we have a firm probabilistic interpretation of what we're doing. So that's just the first step of the EM algorithm. Remember that the first step of the E step of the EM algorithm, the second part of the E step, after we update each of these Q distributions, is to calculate this expectation. So in that case, we want to calculate this thing, where we are now summing over the possible values for each Ci. And so that turns into this. In the previous slide, we had a sum where we had this term here. Now we take this term and we replace it with what we've defined it. So this is just our shorthand. But now we have the sum over each observation, where we evaluate the log of the likelihood of the data coming from each cluster. So that's this term, the log of the likelihood of the ith data point coming from the kth cluster, plus the log of the prior probability of it coming from the kth cluster, so that's equivalent to the log of the joint likelihood of the ith observation coming from the kth cluster and it coming from any point coming from the kth cluster. We take that log and we multiply it by the weight that we assign to the kth cluster and sum it up. So this term is simply equal to this term, where again we are going to ignore this part because it's simply a constant. It's not going to change anything. So we can write this as the log of p minus the log of q. We can separate these two terms, and then this term is not going to involve the parameters that we're interested in updating, so we're going to ignore it and simply look at the log of this term here. And again, we replace q with what we've defined q to be. Okay, so we can actually write this out. We can expand what this is. We can write out the Gaussian form for it, and then get this this function that we want to maximize. Remember, we called this L last time, not Q. And so then we maximize L with respect to pi, mu, k, and sigma k for each k.